And I'm just titling this derivatives of other trigonometric functions. We're going to be extending our skills to include derivatives of the other 4 trigonometric ratios rather than just sine and cosine of rotation angles or x. We're going to be looking at tangent of x, cotangent, cosecant, and secant. And we're going to continue to apply implicit differentiation. As a warm-up, even though we're going to have a rule for this, I think it's important that you know where the rules come from. So we're asked to differentiate cotangent of x with respect to x. Well, we can write cotangent of x as a quotient of cos of x over sine of x, just using a quotient identity. And since we already know what the derivative of cosine of x is with respect to x, and we also know what the derivative of sine of x is with respect to x, this should be pretty easy. We're going to use the quotient rule. The derivative of the numerator is negative sine of x times the denominator, which is sine of x, minus the numerator, which is cos of x, times the derivative of the denominator, which is cos of x. And this is over sine squared of x. I think it's pretty clear what's going to happen here. When you factor that negative 1 out of the numerator, you're left with 1, because you're going to be left with sine squared of x plus cos squared of x. I'll just show this, though. I think, again, at this level, given the question that was asked during the quiz, and my response being, well, the amount of detail you need to show when you're working with identities is less than 30-1, maybe you can get away with not writing it. But I think if you're going to show your work, that would be a necessary statement. And this is over sine squared of x, which simplifies, of course, to negative 1 over sine squared of x. And we would much rather, even though you might think it's not the case, we would much rather work with a reciprocal trig ratio to avoid fractions. So rather than writing negative 1 over sine squared, since the reciprocal of sine is cosecant, the reciprocal of sine squared is cosecant squared, which means we've come to this conclusion. The derivative with respect to x of cotangent of x, I just want to go back and make sure you get this. I'm sure you do. We differentiated cosine of x over sine of x, but that's cotangent of x. So we've differentiated cotangent of x, is equal to negative cosecant squared of x. And I think it's pretty obvious that if you came in tomorrow and I said, what's the derivative of cotangent of x? You could say to me, it's negative cosecant squared of x. You don't have to do this every time. It's kind of like teaching a grade 4 student why 102 divisible by 34 gives you 3, I think. Yes. And you could maybe teach them to do it with Smarties or some kind of model, but sooner or later they're probably going to recognize that, oh, 102 divided by 34 will give you 3 every time. Okay. Is that right? 3 times 34 is 102? Okay, good. So we could do the same thing with the other ones as well. We could do the same thing with tangent, for example. And we would discover by breaking tangent of x down into sine over cosine, we would discover the derivative of tangent of x is secant squared of x. But if I take this statement and I extend it with the chain rule for situations where the argument is no longer x, but the argument is a function of x, then the chain rule says, since the derivative of cotangent of x is negative cosecant squared of x, the derivative of cotangent of u is negative cosecant squared of u times the derivative of the argument. So all of these things that are written in that table part way through the page we're on, was it page 9? About 2/3 of the way down, all of these things that you're looking at here are the chain rule statements. And again, if you stop and think about this now, remembering that the derivative of sine functions are cosine functions, the derivative of cosine functions are negative sine functions, that's fine. You can live with that. You get to post-secondary and your instructor or your prof or whoever it is says, well, no, you just have to know these. Well, then you have to, put your nose to the grindstone, as my dad would say, and memorize them somehow. Okay. I think it's a matter of accidentally memorizing them by working with them enough. I couldn't tell you what they all are right now. For example, I think I do know. I think the derivative of secant of x is secant of x tangent of x. I believe the derivative of cosecant is negative cosecant cotangent. Yes? So, I have memorized them, but it's not, I had to really dig deep in the back of my brain there to pull those out. Because I haven't looked at these. I haven't even looked at these today. I haven't used them for almost a year. So you will get used to these. However, you will be given them for exams. I don't know why I have them there again. Let's just get to it. What is the derivative of secant squared of 2x? This is just really good practice in differentiating and using your rules of differentiation. This function, whatever it looks like, means secant of 2x quantity squared. And this kind of goes to the question that Gabrielle asked about at the beginning of class before we wrote the quiz, where I had to really think hard on the chain rule, that we started here and then we had a link and a link. It's the same thing. The outermost operation, the big picture, is this is a power. It's a power of secant of 2x, because secant of 2x is raised to the 2. So dy dx is found by wrapping the 2 around the base, or the argument of the operation, and the argument stays the same. In this case, it's a base that stays the same. You drop 1 from the exponent. That's the power rule. But the power rule in its most general sense also says, as do all rules, you then multiply by the derivative of the argument. That's the chain rule. The argument is secant of 2x. What is the derivative in the most general sense of secant of a thing? Secant of a thing, tangent of a thing. So right now what we're talking about is this. We're talking about that, but of course the chain rule is going to apply. We're going to have to multiply by the derivative of the argument of the secant that we're differentiating. So the derivative of secant of 2x is secant of 2x tangent of 2x, and then I have to multiply by the derivative of the argument. I'm looking over here. It was the secant of that thing. I'm not looking here. I could, but it's not what we're really doing. And that, of course, is 2. Now, you might, so does anybody have any questions? We're okay with that? And if you want to be really pedantic, which means almost psychologically perfect, when we found the derivative of 2x to get that 2, we were finding the derivative of 2x to the 1. We wrapped the 1 around the x to get 2 in front. It's x to the 0, which is why it's 2. Then you would multiply by the derivative of what you wrap the exponent around. But we're at the end of the line. As soon as you get down to the x, you're done. So we simplify this. I've got a 2 here and a 2 on the outside at the front. I get dy dx equals 4. I have a secant squared of 2x, which is interesting because I had a secant squared of 2x to begin with. I have a secant of 2x here and a secant of 2x here. So that's secant squared of 2x. And I have a tan of 2x. Sooner or later, students start to say, well, do I need to write tangent as sine over cosine and secant as 1 over cos and simplify it? And the answer is no. Because if secant times tangent simplified, I wouldn't tell you that the derivative of secant is secant times tangent. doesn't simplify, otherwise I would have it simplified here. And the fact that I'm squaring the secant in my answer down here doesn't change that fact. Are we okay with that example? All right. What do we got here? X squared cosecant squared of x. So a mixture between, say, a polynomial part, x squared, a polynomial factor, and cosecant squared of x, a trigonometric. So we're going to have to use the product rule, the product, of course, being the product of x squared and cosecant squared. The derivative of the first is 2x times the second, which is cosecant squared of x. We're okay with that, I hope. Plus the first, which is x squared. And the biggest mistake here is to jump the gun in differentiating something like cosecant squared and going, oh, the derivative of cosecant is negative cosecant cotangent. I might as well give you this little abbreviated formula sheet right now, but I think that's right. So then what some people will do is they'll say, well, the derivative of cosecant squared must be negative cosecant squared cotangent squared or something. But cosecant squared of x is first and foremost a power. You have to use the power rule. So I'll give you this abbreviated sheet. There'll be more added to it later. I'll just give it to you now so you don't have to flip back and forth between pages in your handout to see what these 6 trigonometric derivatives are. So this is very similar to, in the previous one, we had secant squared of something. Cosecant squared of x is this. So we wrap the 2 around the cosecant of x. And this cosecant of x that I've just written is the argument of the power, and we're applying the power rule, so the argument doesn't change. I drop 1 from the exponent. We don't need to write 1 there, but I'm going to. Now I multiply by the derivative of the argument of the operation whose rule I used. I used the power rule. The argument of a power is the base. That word argument is a very useful word. If there wasn't a word for that thing, it would be very difficult to explain. So I now have to multiply by the derivative of cosecant of x, which, and you're my eyes here on this, which is negative cosecant x cotangent x. Thank you. And then I have to multiply by the derivative of the argument of the cosecant of x, but that's just x. So I'm done. I'm at the end of the chain. And now I can factor, I guess I can factor a 2x out, and I can factor a cosecant squared of x out. Because I have a cosecant of x here, not what I wanted to do. I have a cosecant of x here, and I have a cosecant of x here, which is cosecant squared of x. So I can take out of each term a 2, an x, and a cosecant squared of x, and have left 1 minus x cotan x. I want to multiply that in my head to make sure I didn't miss anything. 2x cosecant squared of x times 1 gives me the first term. If I multiply that second part out, I get a 2x squared. I get a negative. I get a cosecant squared, and I get a cotangent of x. It looks fine to me. Listen, at some point in your calculus career, if you go far enough, you will be doing detailed analyses of the graph of this function. Now, we don't even know what the graph of cosecant of x looks like. We don't study that in Math 30 even. However, at some point, you would need to be able to determine critical values of x. And it would be at that point that you would write this this way, you wouldn't write it this way in your answer to this question. But if we wanted to go further, you would write it this way, so then you could eyeball the denominator and determine critical values of x that make the denominator 0. You can see that x equals 0 is a critical value of x. And then you would have to eyeball the top, the other part of the top, but you would end up having to solve this equation, which is complicated. I don't know what else word to put. When you solve a trigonometric equation that has trigonometric pieces and non-trigonometric pieces, it's sticky. Okay. We're not going to go there. I'm just pointing out that there are further things you could do. At this level, you can think of the lesson of my little discussion here as being this. At this level, you're finding derivatives for the sake of finding derivatives, basically, with a lot of these things. So this is our answer. This is good enough for what we're doing. Next one, cotangent squared of sine of x. These questions are not really that complicated. They're not, what's the word? They're not massive in the scope of the math. But you have to follow the rules to get the right answer. This is a power. It's a square of something, right? You probably don't need to see it written this way. But that's what it means. And what's in brackets is not a product. What's in brackets here is not cotangent of x times sine of x. There's no x after the cotan. It's just cotangent of sine of x. So I wrap that 2 around the base or argument of the power, which stays the same. I drop 1 from the exponent, and now what I need to do is multiply by the derivative of the argument of the power. In other words, what we used to say up until maybe even the day before yesterday, we have to multiply by the derivative of, quote, what's inside. Okay? But it's the argument. So, what I've highlighted is what's inside the power. The derivative of cotangent of an argument is negative cosecant squared. You guys are nodding. So this is negative cosecant squared of sine of x, which stays the same. And now we need to multiply by, and this is why I said what's inside, now we need to multiply by the derivative of what's inside. When we did that here, at this point I said we multiply by the derivative of what's inside the power, because we just finished the power rule. Here we have to multiply by the derivative of what's inside the cosecant, which is the argument, well, what's inside the cosecant squared. Or better yet, what's inside of the cotangent. So we need to multiply by cosine of x. And sometimes this happens, and you've seen me do this before, where I slow things down and I start talking about this piece too long, I lose my focus on what I was just doing. And there's a rhythm to it. So I'm just going to go back to the beginning and talk my way through it again. I wrap the 2 around cotangent of sine of x, which stays the same, drop 1 from the exponent, multiply by the derivative of cotangent of sine of x. The derivative of cotangent of sine of x is negative cosecant squared of sine of x. Then I have to multiply by the derivative of sine of x, which gives me a cos of x. Then I have to multiply by the derivative of x. That's it, we're done. I don't know how you want to order these things. It would probably be in most modern textbooks written this way. I shouldn't say that. It doesn't matter. Generally speaking, lower degrees come first in a term. And I'm putting this one, even though it's a degree 1, I'm putting it second, because it's a little bit more complicated. It's more nuanced than just cos of x. And I don't know why I put brackets around the x for the cos of x. You certainly don't need to. Are we okay with that one? Okay, a little bit of implicit differentiation. Cosecant of y equals sine of x plus y. So what is the derivative of cosecant of y? I want to say that it's negative cosecant of y cotangent of y. Except it's not really. There's something else. What do we need to do here, Jay? dy dx times the derivative of the argument. The argument of cosecant of y is y, so the derivative of that argument is dy dx. Equals sine of x, well that's nothing. Well, it's not nothing. It's cos of x, but that's easy. Plus y, I don't know if you noticed, but I tried to, when I typed this out, I tried to really move the y away from the sine of x. I don't want anybody to get the mistaken impression that that's what this means. If I had my way, that would always be written as y plus sine of x, but it seems to almost always be written the other way for some reason. Okay, anyway, plus the derivative of y, which is dy dx. Move our dy dx terms to one side. I think to minimize the number of negatives, this is the way to go. And if you've come this far with me on this question, and I think you guys all did well on the quiz, looking at them as I collected them, you understand what needs to happen is you factor out the dy dx and divide. Okay, so now I'm going to have dy dx equals negative cos x over 1 plus cosecant y cotangent y. I mean, whatever that means. It's not that it means something. You would use it to find slopes of tangents or analyze relations in terms of increasing and decreasing values. Any questions with that example? That's it.